So today we're going to introduce another language, which I have kind of titled the talk here Modern Fortran. And the reason for that is that I'm not going to teach Fortran 77. I will teach Fortran with the modern features that the language has. Then it's compatible with old Fortran as well, so that's no problem. But just kind of, I don't go through too much about fixed format, punch card style, source code editing, so it will be more modern. So why modern Fortran? One thing to note is that Fortran is a standardized language. So it's actually an ISO standard, and there is a committee that is working on the standard. So it's compiler vendors are part of this, and there's also researchers parts that define this language. Same thing as C++. Python is actually not a standardized language. It's developed in the community, but it's not an international standard. But Fortran is. So it was standardized. It continues to develop. The latest version we have of the Fortran standard is Fortran 2023. They're a bit slower in releasing new standards than C++ because the standardization committee for Fortran is smaller. There's a smaller community around it, so it takes some more time. It's one of the bigger goals in the standard is that to be backwards compatible, which is also something that can it's not always a positive way. Fortran has been backwards compatible with a lot of old features as well. So they take a long time before they actually deprecate things in the standard, which is good if you want to maintain your code for many years, but sometimes it can also be, it hinders the language. But what I said, you can, even if you can't compile a Fortran 77 source code using a modern compiler, you can always link. So they're link time compatible. So usually that's not a problem. You compile your Fortran 77 code with older compilers and link together. That's no problem. Fortran is also very geared towards high performance computing. So it has built-in support for arrays, which is something that C++ doesn't have as much as in Fortran. C++, for example, has support for one-dimensional arrays. Two-dimensional arrays you have to construct using pointers. 1, 2, 3, and higher dimensional arrays are supported by default in Fortran. As I said, array is a native data type. And there's a lot of functions for working with arrays, and also many language constructs that are geared towards array. And you will see some of the features that I have in Python with slicing is also available to do in Fortran. In the recent years, there was also added support for structuring your code using modules, which means that you can, just like in Python, you can collect your code into logical modules that you can link together. So in older Fortran, the tradition was that you separately compile every function into as a separate source code and then link together. And that has also some disadvantage because it's harder to check the data types. Recently also, I think it started with Fortran 2008. Fortran is fully object-oriented. So you can actually do most of the stuff you can do with C++, you can do in Fortran as well. Also, I think the next version of Fortran, I think it's coming in 2026, will also have support for generic programming. So they're modernizing the language all the time. And also, that's my opinion here, it's the perfect language for creating Python extensions. So there is a tool I will go through in a separate lecture here called F2Py, which can take a Fortran code or a module, translate it into source code that you compile that creates a binding for Python. And then you can use your Fortran code just like any other Python module, but it's compiled and optimized. A little bit of history here. So I will go through this quite quickly, but this is an old language. I think it has been one of the first actually high-level languages that was developed from the beginning. So already in 1954, there was something that would resemble Fortran. But then it has been standardized. So already in the beginning, they thought it was a good idea to standardize. And the reason for its existence was that researchers were tired in implementing their computational codes for every computer platform that was developed. And also it was really hard learning machine code or assembler for different architectures. So they wanted something that could translate to these different architectures. And Fortran stands for Formula Translator. So you have this idea was to translate your computational formulas into code. Fortran 77 is still widely used and one of the most commonly used Fortran codes. In early 90s, there was a big leap made, and that is the Fortran 90 standard. And that added a lot of features to language, such as you don't have to have any line numbers, free format source codes, but it was fully backwards compatible. So they didn't remove any old stuff. So you could still compile a Fortran 77 code using a Fortran 90 compiler. They also tried to kind of remove the legacy using a special language called F, where they actually removed the Fortran 77 legacy code, but that never became anything because it was too hard of a shift. And then you see here that we have regular intervals, you have standards here. And now they have, I think 2026 will be a major revision again. And we have minor revisions here between. So this is just to kind of give you a comparison to other language. This is a Pascal source code for an application. And it has semicolon, it has function, begin, end, for loops, and so on, just to kind of give you an idea of what kind of a modern language could look like and compare that to Fortran. I'm not sure why that. And this is a C version of the same program. You can see here that you have function declarations, you have type declarations, you have curly brackets that begin code blocks, you have a for loop, and you have print statements. This is what Fortran looked in the 50s. Very rudimentary. And you can also see here that you have this kind of fixed columns here. And that was actually because every line was defined from a punch card. And there were strict rules here that the first column was for comment. So you put something in the first column, that means that the row was considered a comment. A certain number of columns were row numbers or line numbers. And you can see here that the constructs have with loops has a starting point, end point, and exit parse here. But you have here, like, you can define a loop variable. You can define formulas. You can do if statements. And just this here was very, very far away from machine code. So in this way, you can actually create really advanced computational codes without locking it to the platform that you're running it on. Fortran 1, we got some more features. You can define your own functions. You get arrays. You get format codes. Little bit more expressive syntax. Formatting code here was actually very similar to what you have with Python strings, format strings. So you can define a format code, and you can use that when you print out here. So I10 here, that defines the format here, and then you can use that when you print out stuff on screen. Fortran 77, then you remove the need to, you only have to specify one line number here, and that is the continue statement of a do loop. If statements here were kind of self-contained, and if so, starts to resemble a more modern language. And this is how modern Fortran looks like, or Fortran 90 and above. You have this program contains here, so you have the main program here. The contain section here, I will go through this more in detail later, will have your subroutines, and then you have end program program name. You also have, there is no line numbers, so it's a free format language. You can have indentation. You can declare data type precisions here, and so it's a very more like Python language in its design. Then I will go through some parts of the source form. So Fortran 90 and above, modern Fortran is compatible with older forms of line codes as well. So there are two ones. The free form, this is according to the standard. So there are many compilers that can handle longer lines than 132 characters. But the standard says 132. So if you want to be correct, if you have a source code file, source code line that is longer than that, it's not guaranteed to be compiled. But if it's shorter than 132, it will guarantee to compile. In fixed form, which is the format used in Fortran 77 and in Fortran 90 as well, you have code in position 7 to 72. You have line numbers in position 2 and 5. You have comments here in position 1. And the character in position 6 will be a continuation of a line. Comments can be placed anywhere on the line. You can continue your line anywhere using the and character. You can have multiple statements on a line by using semicolons. In Fortran 77, you can only have one statement per line. But you can compile modern Fortran with fixed form as well, but I'm not going to show any examples of that. So free form is the source form we are going to use in this course. Yeah, you can see here some of the examples. Here you have and here, that is for continuation. Here as well. Here you have semicolon to have two statements in the same line. More comments here. You can place comments here wherever you want, after a line, between lines, and so on. The structure of a Fortran program. This is the basic syntax for a program. I showed you this before. Every bracket here is optional. So the smallest Fortran program you can write is end. So you need to have end. Otherwise, all other stuff here is just optional. But I would recommend that you use it because it makes your code more readable. So usually you program and you give your name here, and you give end program and the same name here. Then you know that, okay, this is the end of this program. The contain section will return in modules as well, but in the main program here, you can have subroutines that are used in the main program. And then you have specification statements and executable statements. And this is also a difference from Python. In Python, you can declare variables wherever you are. You just declare a equals to something, then you have a variable. In Fortran, you have to declare all your variables in the beginning of your function, beginning of your program, and then you have executable statements. So there is a clear division between specification and executable. You can of course assign variables wherever you are, but the types of the variables, and they have to be declared in the specification statement. Okay, so how do we run and compile Fortran code? So going from a source code to an executable. And Fortran is very different from Python in how you run your code. Not so much how you write code, you use an editor, but how you actually make something that you can run on your systems. So first we have to start, what is a program and executable? So an executable code, that is a binary file containing machine code. So every processor reads instructions just binary or like numbers from the disk, and it executes, and every instruction has a number and followed by parameters, and that is often called machine code. And that machine code is also requires you to have references to libraries in your system. So it has links down to the system to do things like printing on the screen, writing to disk, interacting with the operating system. And then also it has links to external libraries. So for example, if you're using some kind of Intel math kernel libraries, you have links to that, and all of that goes into the program executable file. So it has machine code, it has links to system libraries and links to external libraries. That goes together in a single file. So how do we build a program? You can, of course, hand code machine code, writing the numbers off one after each other, but then you have to know all your instructions of your CPU. And today, these are extremely complex. The next step over that is, under that, is to write something called assembler. An assembler is kind of a instead of you write numbers for the instructions, you write mnemonic codes that represent the commands, like load accumulator is LDA, for example, or load X LDX, or similar like that. It's still machine dependent, but it's more human readable. To make it even easier, you can use Fortran. And then you use something called a compiler that takes your source code, compiles it to machine code, and then links it together to a executable that can be executed directly on the processor. The Python code is a bit different because that uses an interpreter. So it actually compiles every line when it's executing. Sometimes, I mean, it has an intermediate step where it pre-compiles your script code and reads that instead of reading directly from the source code. It's quicker to kind of, it's called, you get these PyC files, which are a precompiled version of your source code files, but they're still executed one line by line. But it's still not executable. And every line is translated to machine code and executed. But it's the interpreter's responsibility to do this. In Fortran, you do that in a single step, translating that to machine code, and then your executable is standalone. It has no requirements to have a Fortran compiler anymore. It's a separate program that can be run anywhere, and you can't even see that it's a Fortran code anymore. So you create an executable in 3 steps. You write the source code, of course, and you compile source code to something called object files. And you can compare that to unlinked machine code. So it's machine code that has links that hasn't been resolved yet. So, for example, there is a call to some routine, and there's just a reference here. Here I will call this thing. And then in the final step for creating the executable file, all these objects files are combined together in the executable, and all these calls are resolved either to an operating system library or to an external library. And that combines to an executable file. And that file you can run directly on your operating system. So this is a more highlight version of the steps here. So on the left side here you have the source codes. So I have multiple source code files. The compiler translates each of these source code files to object code, so unlinked machine code. And then the linker is responsible for combining these object files into an executable. And the linker is not necessarily connected to Fortran. So when the Fortran compiler has finished, it has created these object files, and these are can be linked by the operator directly. So you don't need a Fortran compiler anymore here. And here you also have libraries, which also are object files, and combined together they form an executable. So on Cosmos, the machine we have here, we have a lot of Fortran compilers available, and you can find them in different tool chains. So we usually think 2 or 3 times a year we build a tool chain from the latest compilers, and you can get them using the module FOSS 2025B, I think, where the latest version is. That loads all the necessary search paths that you can compile. We also have Intel compilers, which you also can load a bit different syntax, but they're still there. You can search them if you are on the desktop on the Cosmos machine. You can type ML browse, and then you can get this module browser here. And here you can see that we have this bit old picture here, but you can see all the tool chains we have available. And the reason we keep these tool chains is if you have built a program 2 years ago, you can still rebuild it exactly with exactly the same modules that you built it for 2 years ago. You just switch modules here. And you can see when you load a toolchain, you don't only get the Fortran compiler, you get all the requirements that is required to build scientific codes here. So the FOSS toolchain doesn't only contain compilers. Compiling Fortran code, as I said before, you write the source code. You use the F90 extension. I usually do that. There are some other ones you can use as well, but just to make it easy, I use Fortran 90. You type gfortran if you're using the GNU compiler, -c, and your source code file. That will generate mysource.o. You can have multiple source code files here in gfortran c, source code file 1, source code file 2, and then you get 2 object files. Next, you have to link them. And if you have only a single source code file, you can do gfortran mysource.o. That will generate an out executable, which kind of is not the one you want. So if you don't give it a name, you always get out. But if you add -o, myexec, you can give it a name, your executable file. And the executable file, that is standalone program that you can execute. It doesn't need a Fortran compiler anymore. It will execute anywhere. The nice thing with Fortran is that you actually don't have to use a linker. You can use gfortran here. You don't have to do this separate link step. You just give it the source codes you have, -o, and the executable, and it will do both the compiling and linking automatically in one single step. If you want to run Fortran on your own computer, I would say the easiest way is to use Qt Creator if you're on a Windows machine. Because Qt Creator, you can install that and get the complete tool chain installed for you. The important part is when you install Qt Creator is that you go into Customize, Qt, and select MinGV 13.1.0. If you're on a Mac, there are some links here how you can install the correct packages for your Mac and Linux. But for Windows, it's important that you install the MinGV 32 toolchain. Then you get the compiler as well. I will show you some example you can compile. See here. So on Windows, you also have the possibility to run Linux on your own machine. So you can use something called Windows Subsystem for Linux, BSL. Then you get a terminal where you can run Linux. So I'm in here in a empty folder, and I will just create a Fortran file here, myprog.f19. You can use any editor for that, but myprog. So this is the standard print statement in Python or in Fortran where you don't want to write to disk, you just want to write to screen. You can do print star, comma, and then you can list variables. Note there is no parenthesis in this command. Then we end our program here. End program myprog. And we save this. If we list our files here, you can see I have a source code file here. Then I can type gfortran. I can do just, if I want to link, I can do the compile here, myprog.f90. If we list here now, you can see I have a .o file, and that is unlinked machine code. It's not very many bytes. It's only 2072 bytes, so it's really relatively small. Then I do gfortran myprog.o -o myprog. This links this together to a single file, an executable. And now you can see I have 3 files. Myprog is green here. That means that it's an executable. Now it's 16 kilobytes. So now I've added some other additional parts to the code. And now I can run it by typing ./myprog. And you can see I get some code out. Myprog is now completely standalone. It's a completely separate application. Doesn't need any Fortran anymore. It will run as a binary executable directly on the processor. I can also use Qt Creator. There are instructions on the web page how to install Qt Creator with extensions for editing Fortran as well. So here I can go to File, New Project. I go to Non-Qt project here, and you can see here I have a plain Fortran application. So I just choose. I will do, let's see here, myprog again. Now it will create, and you have to check CMake here as well. That should be default. And then I choose. I just see this one here. So now it actually creates a Fortran program for you automatically. Not so functional, but still. And then you can do down below here you have run, you have debug. Let's do run here. And you can see here it prints out hello Fortran here below. So in this case, you can do a lot of this functionality that you need in this course to do Fortran. You can also add file, new file. You go to Fortran, Fortran module file here in this case. Choose my module. Now you see it added a module file. So I will go through modules later. So I have 2 files now, and I can build it here again. There is a hammer here that builds your program if you just want to see if it works. You can see here building Fortran and my module.f90, and then I can run it here again like this. Oh. So Qt Creator can be a good help to if you want to do work at home with your assignment. But you have to install, if you just install Qt Creator, you will not get the Fortran extensions. There are some links how you can add these this integration into Qt Creator. It's also possible to, for example, do some debugging here. So let's see what we'll do. So I can, if I click here on the left line here, you can see I can get a breakpoint. Then I can do the play button here with a small bug symbol. So if I run this, you can see the environment changes a bit. And you can see there is an arrow here standing on the print statement. And I can do, here below you can have continue, that will run your code until end. You can stop your code. You can step over, which is, it executes the function on the line and continues to the next line. There is step into. So if you have a function press step in, it will go into that function and continue execution there. If you don't want to be in that function, you step out and it will go back to the calling routine and continue there. So let's see if we do step over. You can see it goes to the next line, and you can see here it runs your code step by step, and you can see the output here is coming out here in the output section. And then it exits the code here like this. So good to create a completely interactive environment for Fortran development. So let's go to how you develop in Fortran. So we start with variables. And you already have used variables in Python. They are not that dissimilar to Python. However, in Fortran, you have to deal with types. So a variable can't change its type during the execution of your code. So variable are name, storage location in memory that can hold values, which can be modified during the program execution. The compiler will allocate memory for the variables according to data type of the variables. So variables that are not, I will come into dynamic variables later on, but the normal variables in Fortran will be allocated by the compiler in the executable, so there is space for those variables. Naming, you have 1 to 31 alphanumeric characters, so letters, numbers, and underscore. Variable names can consist of both uppercase and lowercase characters, but Fortran is a case-insensitive language. So variables with the same number of characters, it will correspond to, for example, my var with uppercase is the same as my var with lowercase. So it's case insensitive. Also, the first character can never be a number. Some examples here, valid variable names are A underscore thing, X1, mass, Q1 to 3, time of flight. Invalid variable names are 1A, or a thing with a space, and only an alphanumeric character can also not be a variable. So it's similar to Python, but just remember that there is no difference if you have an uppercase first letter, it's the same as the variable with a lowercase first letter. The base data types, so these are the base data we have. These can be combined into arrays and stuff like that as well, but these are the base ones. You have integers, you have real for floating point numbers, complex for complex numbers, logical for Boolean, character for strings and characters, and you have derived types. So derived types is the way you can define your own data types. Also, all of these the variable types can have different precision, different number of bytes that can represent that number. So you can there are not only single ones of these. You can have integer 4, integer 8, integer long. So you can have specify the precision of each of these data types. You declare them by specifying the type. So type here is real, integer, and so on. Attributes are special character, for example, things that you can tell the compiler that this variable, for example, is a constant. You can add an attribute for that. So that controls how the variable can be used. Then you have colon, and then you have a variable list. So this is some examples of how it can look like. So you have integer colon A, that's a single integer variable. Real, B, that is a scalar floating point variable. Also, if you declare real without any additional flags, it's a single precision floating point. So it's not a double in Python, it's actually a small one. And that is a inheritance from the 50s where storage was precious. So they put default as the smallest variable they can have. Logical, that is a Boolean, like in Python, true or false. You have real, then you can have arrays by specifying parentheses 10. So that is a floating point array of 10 elements. Two-dimensional, 20 by 20 array, two-dimensional array. You can also specify dimensions here as an attribute. So for example, if you want to declare two arrays of the same size, you can do integer dimension c, d. So this is just an alternate form of this declaration here. Character, that is a single character. A character dimension 60, that is not a string, that is an array of characters. So you can't use them as strings in Python. Strings in Fortran, you declare character and the parentheses here, how long you want the string to be, and then this is a character string. This is an array of strings. So there are some differences here. You can't use CHV as a string in Fortran. It's an array of characters. Another, not a variable, it's more a constant. So that name values that you can't change when they have been defined. And the compiler also, if you add an attribute that is in constant, you can't change these values. So we will get the compiler error if you try. You declare a constant by adding the attribute parameter in your declaration. Another thing that you can, as I said before, you can actually define the precision of a variable by adding a parenthesis after its data type declaration. However, this is very system dependent. From the beginning of Fortran, there was no kind of definition on what the floating point was supposed to be. And the floating, you can have multiple different supercomputers have a different floating point implementation. Today is a bit different, but way back it was very different. And the specifiers you specify here are dependent on the compiler and system architecture. So to avoid kind of hard coding in a number in your declaration here that you think means 8 bytes, for example, you should actually use special compiler functions to determine what these identifiers should be. It sounds more complicated than this. So this is our explicit precision specifier. So real 8, in normal x86 architecture, that means double precision. So usually 8, if you have on x86 platform, the 8 here is 8 bytes, and real for that is 4 bytes. Integer for that is 4 bytes. But the standard doesn't say that. Usually it's like that. So if you want to really know or have a platform-independent way of specifying these specifiers, you can use selected real kind, for example. That computes the number depending on the parameters here. And then you can use this constant to declare variables. So in this case, I say I want to have 15 significant decimals and exponential range between -300 to 300. The compiler then we cannot check, okay, what is the best precision specifier for that? And it will set this constant here. So it will do it compile time. Then you can use RK here when you declare variables. And it also, so you can see I have real kind equals RK. You don't have to specify kind, you can just do real RK. Another important thing is that when you declare scalar variables, you need also to use the suffix here RK so that it stores the scalar value with the highest precision. If you forget about that, this will be single precision. So it will try to make it as small as possible, which is not what you want. Just to kind of illustrate this, here I have declared a constant called AP. And two variables with the same precision, like pi1 and pi2. And then I assign pi1 the value of pi up to a certain precision. And then I do pi2, same thing, but with a suffix AP. And then I print them out here. And you can see here that they start to diverge completely in the middle here. So pi2 can represent the complete constants, but not pi1. So that's why it's important to have these precision specifier as a suffix. So make sure that they actually are, you get the entire scalar constant here with enough precision. general type rule. This is not the best size of Fortran. So by default, you don't have to declare any variables in Fortran. There is something called a general type rule, which if you haven't declared anything, variables starting with I through n are integers, and other variables are real by default. But this is not what we want, because this can lead to really bad errors. So what you should do if you write code in modules or main program, that you should use a directive called implicit none at the beginning of a program. That tells the compiler that we require that all variables should be declared. And if you don't, you get a compiler error. But if you forget, I through n will be integers, and we can't specify. You get the kind of the lowest version of them. Variable assignment, real, the precision specifier, and then if you have a scalar value, you add a suffix here. There's also a selection integer kind here, which you can use with ik. Then you put ik here in the beginning afterwards here. It's not that. It's more important if you have a long integer here that you need to specify that. Logical is false and true with the dots here. This is also an inheritance from old Fortran where the standard doesn't specify how many. You can only have 127-bit ASCII, which means that you can't use too many characters here. So they added these dots here to indicate this is a keyword. Strings you declare just in Python. You can have double quotes, single quotes. However, you can't do backslashes in them. You also note that if you want to do a lot of string process, it's probably more good idea to do that in Python, because Fortran, all the strings are fixed size. There is no way of having dynamic strings. They're all fixed. So it's a bit hard to do string things in Fortran. Another thing that you also have to know, when you declare a variable, it's considered undefined. The memory storage is there, but there is no value there. It points to some random memory location. Also, you shouldn't use a variable that is undefined. When you assign a variable, it's considered defined. Then you can use it. But if you use undefined variables, you don't know what you get. You can get a 0, you can get a really large number. So you can really mess up your calculations if you forget to do that. And that is also regards to array. So if you declare an array, it's not zeroed. It points to somewhere in memory. And an array is defined when all elements have been assigned. Then it's defined. See if I can run this example. So you can see here, this is a code. I have A here is defined. S1 is defined. I print A, I can get 42. I print B. By chance, I got 0 here, but it's still not, it's considered undefined. My defined string is printed as string. S2, you get this kind of strange character here. You can see here that it's kind of just luck that I got a 0 here. It could have been some garbage number in memory as well. Also, in the book, the Modern Fortran book online, there is a lot of these try code here. Then you can run your tryout example in Compiler Explorer, which is really nice environment for trying out things as well. So in some cases you can't express everything with the built-in data types. You need something that is not that suits your own needs, and that is a derived data type. And you can create a derived data type combined of the standard variable types, arrays, and other data types. So you create something new that combines other data types. You define them by using a type statement, and then you give your own name of it, and then you give the variables in it. So for example, if you want to do a particle system, you can create your own particle data type. So you can see here I have type, type real, and then I have 4 fields here, X, Y, Z, and mass. And then I do n-type particle. And now I have my own data type. And now I can create a particle P by doing type particle P. And then I can access you can see here I have in Python, this is a dot. In Fortran, it's a % operator. So if I want to access the X element of P, I do P % X, and then I assign a value. And here you can see I print them as well. But you don't have to have the same data type. You can have a mix of data types here in your structure as well. So in this case, I have, for example, a data record here. I have a name, and I can assign them like this and store them. So you can have anything in your derived data types. I just find I can do this section here. There is one problem with this kind of that Fortran doesn't have a real fixed data type. What they are is when you want to interoperate with C++ and C. So the standardization committee in Fortran, they have created a special module called ISO-C binding that contains the mappings from C to Fortran. So here you can see that you have these are constants, just like we did before we selected real kind. C float, C double, C in, C long. And then you can declare your Fortran variables using real, C float, X. Then that is guaranteed to be, the data type of X will be compatible with a C floating point variable. So here you can see I can use ISO-C binding, introduce C int, real C float, real C double. So the double here, the floating point of Python is a double, so that will be compatible with Python as well. And then you can see you can use suffixes here with C float, C double as well. I will stop there. We'll do a short break here. So let's continue exploring the language here. Operators and expressions is of course important in a language that deals with formulas. These are the main ones. You have power of, multiplication, division, addition, and subtraction. And they are evaluated in this order as well, as I said before. Relational operators, you have, of course, you are backwards compatible. So if you encounter any older code, you will probably see the middle column here with .lt, which stands for less than, less equal, greater than, greater, equal, equal, and not equal. So the new operators are on the left side here. So these are preferred when you do modern Fortran. Similar to Python, except to this one here. This is similar, but this one not equal to is a slash equal instead of exclamation equals that you have in Python. You have logical operators, and here we have only the older format here, dot and, dot or, dot not, dot, and or not. Also, just kind of integer expressions. So, for example, if you have 6 by 3, this will not return a floating point. It will return an integer. So 6 by 3 it will round it towards 0. And here are some warning here as well, how they're handled. Let's see here, run these. Yeah, this one, okay, skip that one. So this will be 0 because it will be considered a division here, so it'll be integer division, and then it will become 0. So be careful with that. So Also, if you have different data types and you do expression with those, for example, here you have real b is the resulting variable, and you have a real, which is considered stronger than integer. I here in this case will be converted to a real automatically. Also, all the operators that you have seen here can be used on arrays. So it's very similar to when you're doing NumPy arrays. So you can add arrays together with the plus operator. However, you need to make sure that the shapes of the arrays are the same. Otherwise, you get problems. And also, there is no checks here. So if you do this, it can crash your code because it will. It's not an object that has some built-in safeguards. It's kind of, you need to check that. Some compilers can check this as well. If you add, for example, an array to a scalar, that scalar will be broadcast all elements, so it will be add to every element in the array. Also, the order of the operations in these expressions is not defined in the standard. So if you have add a 1 to all the element in the array, it's the order of that operation is not defined. There's an example. So I have a 10 by 20 arrays A and B. I have a vector or single one-dimensional array of 5 elements B. So if I do A divided by B, you get all elements are calculated like Aij divided by Bij. So if you have V plus 1, so it will add 1 to every element in V. And here you can see I have a 5 divided by V. So this will this operation here, and then it will use a extract a slice of A here, and then I add that together. You can also do logical operator E dot equal B. So that is true if all elements in A is equal to all elements of B. So arrays and matrices. Yeah, it's kind of obvious, but it's a built-in data type in Fortran, which makes it very easy to work with large array structures which is kind of harder in the other languages. You can create arrays both dynamically or statically. So up until now we have only declared static arrays, so that arrays that are known at compile time. But with dynamic arrays, you can allocate them in runtime as well, and that is a feature that was added to Fortran 90. So Fortran 77 didn't have a dynamically allocated data array or any data type for that matter. They also support slicing and assignment different ways. Yeah, here's some examples here. Here you can also see that I have selected real kind here, and I do RK here for the data type specification, and then I have my the size declarations here. These are statically arrays. And here is also a difference from Python. By default, every array starts at 1. But you can actually redefine this. So here I have an array going from -3 to 3, and this is equivalent to these are the indexes then that you can access this array with. So that can be useful sometimes if you want to do some translations, or you want to have a array that is compatible in the syntax of a Python array, for example. So, but by default, they start at 1, so not at 0. Array assignment, instead of square bracket as in Python, you have parentheses, and then the index that you want to assign, and then you give it a value. If you don't give the indexes, it will assign the entire array. So that can be useful. If you want to zero an array, you can do it in a single statement without a loop. However, you should think about not by default zeroing everything in your code, because this operation here is expensive. So you don't want to do that without thinking. For example, if you want to read an array from disk, you don't have to clear it first. You can read it from disk, overwriting the values in the undefined state. So Even if I say you should initialize variables and so to make your variables defined, this is not, you shouldn't do it just by default. You can also assign multiple variables at the same time. So in this case, I have an array of 5 elements, and then you can do v equals 2, and then parentheses slash, and then you list all the values, and with slash parentheses. Not as kind of elegant as in Python, but still you can assign multiple variables at the same time. Slices is a way of assigning variables to rows and columns. So here I have a two-dimensional array 4 by A with 4 by 4. I can do row 2 and all columns. So that means basically I'm assigning a row, and then I have all columns here. Sorry, all rows and first column here. So then I assign the values of column 1 into A. You can also do stuff like this. So if you want to assign a column here of so row 5 and then row 5, and then I can give it a list of values here that I want to assign into that row. I don't know how to explain. Another thing to think about is how, I think I mentioned this in Python, Fortran stores all arrays as continuous one-dimensional arrays. So the 2 and 3 dimension is just a way of how you move within the array. And in Fortran, the default is that you store them column-wise. So if I have an array here, 16, it's just a single array, 1 to 16. I can reinterpret that. If I have 16 elements here, I have 8 rows, 2 columns. They are stored as 1, 2, 3, 4, 5, 6, 7, 8. So column, then I go to the next column, 9, 10, 11, 16. NumPy has the other way around. It starts row-wise, unless you specify that you want Fortran storage, which you can do in array in NumPy as well. And if I have 2 by 8, it's stored 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This I already did. Yeah. Okay, I repeat this. I did a better slide. So basically, this is assigns single row like this. You can also do derived arrays of derived data types. So in this case, here I have my data record here, and I have an array of 5 data records. So this is an array consisting of 5 data records. And here I can use the index operator here to get access to different elements in that array. Conditional statements. So if statements, there are multiple versions, just like in Python. So the first one is just if scalar logical expression, then execute a statement. And the parentheses, you have to have those. So the expression has to be in parentheses, and if the expression value is true, it executes the statement here. So this is kind of a single statement if statement. Then you can have if scalar expression, then, and then execute a block here. And then you end that with end if. So if, end if. But you need to have then here to make this work. Then you can have if, then, block 1, else if, then block 2, else block 3, and then you end the complete if statement with end if. So here's an example here. If you can see our parentheses here, x greater than 1000, then execute this block here, and then you end if. So in Fortran, you need to kind of keep track of your start and end of a block. Same thing here, and then you have here if, then, write, else, write this. If you have a lot of test cases you want to test, you can use the select statement instead. Then you have select case expression, and then you have a case selector. So, for example, select case character, for example, then case A then do this. And then you have also the possibility, if none of these selectors here fulfill this expression, it calls case default. So they can look like this. So I have a value here. I enter a value, and then you can see here that I go case if greater than 1. If it's number 1, it prints this one. If it's between 2 and 9, if it's 10, yeah, and so on. And then if nothing is fulfilled, it will go to the case default, which should be a good rule of thumb to have if you always have a fallback if you have these kind of statements. Then we have to repeat things. The basic construct is the do loop. So you have do, and then you have a variable, starting value, and an end value. And then you iterate over here. And then you can, just like in Python type range statement, you can have a step. Then it goes starting point 2, 6, 10, 14, 18, 22, 26, 30. One thing to note here, you're not allowed to modify the loop variable inside the loop block. This is breaks the standard. So it's not allowed, and I think the compiler will probably complain about that. You can control the do statements as well, just like we did in Python. We break and continue. Here we have exit that exits the loop and continues after the loop. We have cycle to go to the next iteration. Do while, so if you want to loop until a certain expression is fulfilled, you can do like construct. So you have do while, and then you have an expression in parentheses, the block that is executed if the expression is true. It can be something like this. Do while x less than 1.05, and then we do some calculation, and we loop update x here until it's certain that criteria is false, and then exits the loop. So there is a lot of built-in function in Fortran, not nearly as much as there is in Python. The runtime library in Python is really big, but there is some functions here that can be useful. So of course you have all the mathematical functions, conversion functions here like apps. Here you can see you can have that truncates the floating point value. And the same is similar to what you do in Python here. If you want to convert a variable to an integer, you do int and then the variable name. You can convert an integer to a floating point. There's a max function here to compute the max over a number of values. There are some support for matrix functions. So the array support in Fortran doesn't have a class matrix and array. So you work on the array is kind of just a data structure that you can manipulate with expressions. If you want to do a matrix multiplication, you need to use mathmul. There is also a dot product function you can use, and there's a transpose function. So you can't really create really nice matrix expressions, but you can use these to create expressions. So also to note, every function in Fortran can be called with arrays. I already go into a divided by b will be element-wise division here. Square root a, that will compute square root on every element in a and return that into c. And the important thing here is when you work with expressions like this, it's your responsibility to make sure that the arrays have the same shape. If you try to do this on different shaped arrays, you will get a segmentation fault. The program will crash. There is no checks. That's a disadvantage of having a compiled language, that it's geared for speed, not for safety. That you have to do yourself. Some compilers can check for this, but just be aware of that. So I will do a bit more larger example here to illustrate how you design, how you can implement some of these expressions. So This is a very simple stiffness element in mechanics. So I have a set of transformer I have to do to compute this stiffness matrix here. I have a transform matrix J here, which I will multiply K, and then I will multiply with J again. I have the K element matrix here, which has a scalar part here, and then minus 1, minus 1, and so on. And here are some of the scalar parts here. So what I do first is I declare all my variables, the selected real kind. So also note that you can see implicit none. That forces me to declare all the variables. Integer parameter here, that is constant needs to be the first part of the file. And then I have loop variables here, all my constants here, all my matrices, and the J matrix here. I initialize all my variables to defaults. I compute L, I compute all my scalars, and then I construct my matrices. So one thing I usually do is I do it row by row. So in this case, K1 colon equals to the first row, and then I assign these values here. K2 colon equals to the second row, and then you KEL equals to KEL times the scalar value here as well. Then I construct the J matrix here. First row, these parameters. Second row, these parameters. And now I'm ready to calculate my final matrix here. So I start from inner work myself out. So I have transport J, matmul times K element matrix. I have matmul transpose J, and then JG here, and then I have auto matmul here as well. Not super elegant, but it's single row. You don't have to do any loops here. And then I just print it out here with some nice formatting. I get this. So this is how I try to, I can, basically if I have some Python code, I can convert it here and do similar operations in Fortran that I do in Python. So next, let's talk about how you structure your code. So these are the building blocks of creating a larger program. So for smaller things that are utilities, you can get by with just doing a program and contains and then functions or subroutines. But the program gets larger, you need to kind of divide up your problem into blocks that you can reuse, but also maintain in a nice way. I've already covered here. You have the program contains end program. That is the basic. The thing you need to do a single executable. You need a single executable can only have one program structure like this. So you can't have multiple source code files with multiple programs. You have only one in a single executable. The stop statement that stops program execution, and with warning here, you can use that in all program units. So that will stop the code directly. A good idea is that if you want to have a centralized error handling, is that you should kind of have a stop statement only a single place in your code, so that if you have an error statement in a function, you should return from that function with an error statement and then handle errors centrally. But you can also add a code to the stop statement so that you can query some error state as well. Subroutine and functions. So subroutine is a named block of code that performs certain task. It can be called from different parts of the program. You can have different number of arguments. You already know that's Python here. Arguments can have both input and output. In Fortran, you have a distinction between a function and a subroutine. So a function is very similar to subroutine, but returns a value. They have different keywords. So in Python, you have the def statement. In Fortran, you have some subroutine and function as keywords. There are three kinds of subroutines. They look the same in the declaration, but it's way how you compile and link together your code. You have external subroutines. These are often placed in separate source code files and compiled separately. As an implicit interface, it can be implemented in other languages as well. So any object file can be linked to Fortran code if you have the same data types, they should link together. Internal subroutines, there are those that are inside program units in the contain section. Module subroutines, there are subroutines and functions that are inside a module. This is the syntax. You have start with subroutine, give the name, and you have a dummy argument list. And dummy, that means that just these are not real variables, they are just kind of representing variables somewhere else. You have the same structure as in other code. You have to start with the declarations in your subroutines, and then you have your code. And then you have also the possibility to return using the return statement. You can have multiple returns in your subroutine as well. Then you end with end subroutine, and I would recommend to put subroutine name at the end as well, because then if you have a long subroutine, you know, okay, this is the end of this subroutine, but it's optional as well. By default, all variables that you pass to subroutine are passed by reference. That means if you modify a variable inside a subroutine, it modifies the variable outside the subroutine as well. So the arguments refer to actual variables outside. And you have to declare all your arguments in the subroutine as well. So it's not as flexible as in Python. You need to kind of have the variables declared. You call the subroutine using the call statement. So in Python, you can just give the function that will call it. You return the control using the control. So here I have an example here. I have my main program here, and I have a subroutine below here. And I call that with A, B, and C. And you can see here I can have R, B, C here as well in my subroutine. They don't have to correspond to the variable names here. I can also declare, so in this case I have R here is the, you can use the variables coming in the parameter as a declaration of arrays here as well. And the last dimension of an array doesn't have to be specified, because you can always get to the next column by using the number of rows. Yes. But if you modify the code inside here, it will modify the variables outside as well. Function is the same thing here, basically. You declare the function name, and then you return value by assigning the function name a value. So here you also give the type you want the function to return to the left side. Looks something like that. Real function, so this is the return data type. Function here is the reserved word, and then the name of the function, and then you f equals to sin x, that will return the value here as well. So modules is a way of, it's like a program where you have executable statements and subroutines. So you can package global data, variables that you want to be, variables and constants that you want to be available to all your programs, or all the program. Derived data type definitions, operations on the derived data types, subprograms. You can also declare function interfaces, basically declaring how a function should expect. If you want to have a function, calling a function with a function, you can define what kind of interface you want on those. Basically declaring a function type. Name list or something we go when we come to file management. So for example, it could be, my recommendation is if you have functions that handle a single kind of area in your code, put those in a single module. So for example, interval arithmetic could be a single module. You can have your finite element function of a certain type in a single module, and you kind of divide up your code in that way. Looks like a program. You have, instead of program, you have module, and then you have contains and module. So the same kind of structure as a program, but it doesn't have a main routine. So you can't execute anything in the module section there, only specification statements. Then it looks like import statement in Python. So instead of import, you use constant. When you do that, all the public parts of the module will be available to your code. So it's almost like importing a Python module. So in here you can see that I put all my constants that want to be available in my entire program. I put them here in, so integer kinds, real kind. I put them as constants in my constants module. So instead of doing all these ugly declarations here in the beginning of my program, I can just use constants. And then you can have a single place in your program where you can modify the precision of your data types. And then wherever I want to use these constants, I just use constants. What you can also do is that you can actually hide things in the module. So by default, everything in the module is public, but putting real private will hide that for the user of the module. So the variable declared private can't be accessed by the calling module or the using module. So in this case, I have a subroutine here, bar2e. It's public. I could make it private if I want to hide it as an implementation routine that is not supposed to be used by some other usage, other program. So here I have use stress. I can do call bar2e, but I can't access the private variables. Yeah, then I go back to the parameters again here. As I said, they are passed by reference, and changing a parameter will change the variable in the calling routine. And the reason for doing this is speed. Much of things in Fortran has to do with speed. It's easier to call a subroutine with references because you don't have to copy anything. You just give it, here are my actual variables, please do whatever you want with them. But you can have some undesired side effects. So suppose you have a Fortran library that solves a linear equation system. You put in your vectors that you want to solve, you run the code, and all of a sudden your input variables have been changed. And that's not an uncommon problem in many Fortran libraries. They use your input variables as work arrays. And if you don't document that, you don't know about that, and you call the routine and it has destroyed your variables, the data of your variables. Yeah. So in this case here, I have a program here. I have a subroutine. These are separately compiled. So this is not a module. And if you have separately compiled source code functions and subroutines, you need to be very explicit in your declaration. So in this case here, if I want to pass A here as an array, I need to give it the rows and columns of that array. Same thing with V. So in this case here, I declare these as integers, and then I do the dimension of A here using these parameters. And you don't have to declare them exactly the same way. In this case, I declare A as a single one-dimensional array, just that it has the same number of elements. That's the important thing. So these can be separately compiled and linked together. Yeah, so as I have two flavors here, implicit is separately compiled F90 files. The risk with those is that you can actually link together functions that are not compatible. And it will work perfectly fine until you call the routine or you look at the information. You will probably get some garbage data because they were linking together data types that didn't fit. The explicit subroutines interface is in Fortran 19 above, and that is all the subroutines that are in modules, contain sections, or interface declarations. And in this case, the compiler has all the information to be able to handle the calls and pass some to make sure that they work together, and it also can simplify the calling interface. You don't have to pass all the variables over to the module, which I will show here. So in modern Fortran, using modules, you can declare variables using colon, comma, colon, or colon in your subroutines. So just saying to the compiler, I expect a two-dimensional array. That means colon, comma, colon, that an array comes in as is two-dimensional. Single colon, that is a one-dimensional. So you get shorter subroutine lists. And you can also query the sizes of incoming arrays using the size function. So this is the implicit interface that we showed before. You compile program, you compile subroutine, and you linker determines if they are compatible or not. There is no check if the actual parameters are okay. With the module interface, I put everything in module utils. And now I can declare A here as just an A. I have an array coming in. I expect it to be a two-dimensional array. I can query the size using size and return here. So this is much simpler than having a very long calling routine here. This is much more elegant. Same rules apply for if you're doing it internally. Everything it contains can have the same kind of declaration. You can have colon, comma, colon there as well. So that this can be seen as an internal module of your program. Sometimes also called assumed shape array. You can do this without modules, but then you have to tell the compiler what to expect. And you do that using this interface declaration here. It's a bit, you don't have to remember. Just remember use modules so that you don't have to do this. Automatic variables is another kind of variable that you can use in subroutines if you want to have multiple variables of the same size as the parameters coming in. They're created on the stack and they're automatically allocated to the desired size. However, they must fit in the stack, and the stack is the local variables are stored in a certain memory location in your running program. It's of limited size. You can change that in your operating system how large the stack will be, but it's limited in size. So you shouldn't create really large automatic variables. So here you have a subroutine here, my sub A, and then I create a B array here that is size A1, size A2. This will be automatically created from the sizes of the incoming A here. So this can be a work array that you need to be able to solve your problem. You have an additional that is the same size of A. So finally, some additional array features that can be good to know. In Fortran 90, the Fortran standard added dynamically memory allocation, and especially regarding arrays. And it's in many problems you don't know the problem until you actually you read the input file and they say, oh, he wants to run 1 million cells. And then I can't if the program have a static array that is only 500,000, you can't run that. So by using dynamic allocatable arrays, you can actually create the arrays on the fly when you're running the code. And that is an attribute that you can add to an array declaration called allocatable. You have to define the amount of how many dimensions you need in the array. So that has to be determined, but otherwise you can set the sizes to whether you want. Another important thing, you are responsible for actually deallocating the memory as well. So when you're not using the array, you need to deallocate it. So for example, if you're allocating arrays in a loop and you don't deallocate in the loop, it will fill the memory of the computer. So you need to make sure that you have an allocate statement and deallocate for all your variables. If you allocate variables in the subroutine, Fortran will actually deallocate the variables automatically for you when it returns. So here's an example. You declare, instead of declaring with fixed dimensions, you use the colon notation that we had before for the subroutines. You add allocatable to your declaration, and then you allocate with allocate, and here you give the fixed dimensions. Could be variables as well, and then you can you deallocate with deallocate. You can also do it in a single statement, allocate and deallocate multiple arrays. Yeah, I already touched about this. You can use slicing as well. So you can use indexes here in your arrays to get sub-objects. You have to be a bit careful when you're doing this, when you're passing them as arguments to other function, is that certain cases it can actually make a copy. It tries to avoid that, but it could be potentially costly to do some of these things. We already did that. Yes, reduction routines. So there are several routines that can do check all the elements of any function. For example, all, if you have logical arrays, you can do true if all elements are true, any true if any element is true, max val, compute the max value of an array, min val, the same thing, product sum, very similar to what you do in NumPy. So here you can see, you can calculate this. You can also query the lower bound of an index, upper bound of an index, the shape of an array, size. We showed that in the subroutines before. Let's see if we can start with this. So just like with Python, you need to get data in and out from Fortran. Reading and writing of files is done using the read-write statements. If you compare to Python, you only read one statement, one row per read statement. So there is no flexibility here. It's either you read and write a single row. First parameter determines where to read and write. When you write to standard input or writing standard output, you can use a star to kind of, I don't care, just send it to the standard output and standard input. Another thing to know is that Fortran automatically converts text in a file to typed variables. So compared to Python, where you have to translate all your reading to floating point, Fortran will automatically convert data in a file to the corresponding data type that you're reading. You can read several variables in the same statement using comma-separated list. You can also have an implicit loop inside a single statement to read, have more flexibility in how you read per line. So for example, here you want to read 8 floating point values. You give read star, that means I read it from standard input. You just put them on a just single statement like this with commas between. But you can also do something like this for I, comma I equals 1/8, and it will read 8 variables. But you could have n here, for example, that would be, then you can have any number of columns. You need to have parentheses around them. You get the same thing for writing as well. If you just want to write a standard up, you can use the print statement as well. So the second parameter in the write statement defines the output format, which means it's similar to what you do with format statement in Python. If you put a star there, it will kind of just output with full precision. So you get really long numbers. And the format parameter is a string describing the output format, just like in Python. And you use format codes just like in Python, but not the same. So common codes here is the brackets are not part of the code. So you have, if you want a string with 10 characters, do A10, integer I, and then a 4 to get 4 character integers. General floating point J, you have the number of the field width and the number of decimals. If you have 6 integers in a single line, you do 6i5. And then you have to have a parenthesis in the string. It's a bit complicated, but so this means that you have 6 integers in a row and a field width of 5. And you have to have parentheses here in the string for this to work. So here's an example here. I have a write statement here. I want to write, first I have 3 strings with the width of 8. So you can see here I have 8, 8, 8, 4 strings of width of 5. And then I have a table here that I want to write. So I have 3 floating point values, width of 8 with 3 decimals, 4 integers with width of 5. In this way I can create a column format output. Looks like this. So you can see here that first field is 8, and the next field is also 8, and so on. So you get them aligned like this. Not as flexible as for Python, but still works. The problem is that you have to be explicit in your format codes, and it's a string. So it's kind of, suppose I have a function I want to write an array that has, I don't know the dimension of it. I query it and I want to create a format and output of an array. It's a bit problematic. But the thing is that you can use a string as a file. So I can write to a string using the write statement. So what you can do then, you can create a format statement string, and then I can print to my format statement here. So this is the target of my write statement. I want a string, an integer, a string, and I put columns here and a G83 at the end here. And then I get a format code which I can use to print out here. So just remember, if you need to have a formatted code for any number of columns, you can create them using this technique. It's a tip. Also, reading and writing to files. So now we are reading and writing to standard from the keyboard onto the screen. Just like in Python, you need to, if you want to write a file, you need to open a connection to a file name and get a handle back, which you can use to indicate where to write. And you use the open statement to do that. Fortran handles 3 types of text files. You have text I/O, you have namelist I/O, and unformatted I/O. Text files are just like in Python, text files. Namelist I/O is a bit like JSON in Python. So you have the key and values, and they are written in pairs, and you define which variables in the name list. Unformatted I/O, that is binary files. So it takes the variables and writes them in binary form to disk. Also, like in Python, we need to close the file when we are done with it to tell the operating system we are finished, so we can write it down to disk. Here we don't have any tricks like with, we have only open and close. So here we have, I open a file. Usually I define my file numbers here, because the files are identified with a number in the write statement. So I define some constants that are in file and out file. Then I open in file, and that is associated with the in dot dot. I want to write in text file, that is access sequential, and I want to read from the file. Then I read and I put my in file here, and I close my in file. If I want to write, I do out file, dot dot, access sequential, action write. And then I write out file and close out file. Reading from keyboard, it's ***, which I covered before. It's you expect input from your terminal or from your keyboard. There is a reserved number here that you shouldn't use in your file. So 5 is actually standard input. So you should avoid that when you declare your parameters here, not use 5. Screen, that is actually write ***, but 6 here is reserved for standard output. So avoid 5 and 6 when you're declaring your file variables. I think I stop there, and then we continue next week, because I don't have a lecture on Thursday.